guest lecture and discussion at the beginning of the tutorial today. Time that would normally be devoted to student project meetings at tutorial. Some of that today will be a lecture from a previous project manager for this course, Kristen Durgasov. Some of you may know her. She works in the department. She was an intern in the department 2 years ago and is now working in one of the labs. She served as the project manager for what I would consider a very successful project team in the version of this course that ran 2 years back. Their team was notable both for its technical success, but also in terms of its sort of gel character, the way in which the team stuck together, achieved high morale, communicated well, etc. So I'll be introducing her briefly at 4 o'clock, and then she'll share some thoughts about their experience within this class. I'll be leaving, and you can have a discussion with her about some of the things you might think about a team, some of the things that are perhaps on your mind, how to structure things, how best to structure meetings, or to run the interaction between the test team and the development team. What is the best decomposition of responsibilities across the team, etc. How did they achieve shadowing to spread knowledge around, etc. So that would be at 4 o'clock. What I'd like you to do is to come up with some ideas for questions for her, so that you can make best use of that time to get advice now that might inform your initial presentation, which is in another 2 or 3 weeks, might inform your decision making about this first deliverable, and in fact the ways in which you interact with stakeholders, etc. So see if you can make best use of the tutorial time today with questions. Okay? So today we're going to be continuing on our discussion about a topic we touched on last time, and that is the issue of testability. I'm going to spend a fair bit of time discussing this issue, which is often new to students, and then we're going to be going into some high-level tips related to the testing process. Ways that you can make best use of your limited resources to really help verify correct program operation, help identify weaknesses in the program, help identify usability issues, etc. So we're first going to talk about testability. Now, who can remember from our last class what testability is? When we say testability, what are we talking about?
The ability to create tests for even set code?
Yes. So very good. That's really an excellent start. And the ability to create effective tests and to create quality tests. It's one thing to facilitate creation of any tests. It's another to facilitate creation of tests that might really catch high-risk issues, allow you to really determine if an algorithm that's otherwise a black box is really operating correctly in its internals, like it should be, for example. Whether the system will react properly to a rare error that can be hard to reproduce. Turns out that by cleverly building in some types of functionality, by supporting general principles like good specification-oriented interfaces, by incorporating modular design, and by structuring the program so that you're separating interface from implementation, among other things, you can enhance testability. So I'll talk about some sort of best practices that will aid with that and help you to understand some practical things you could do, say building test hooks that can help enhance testability. So So just as a reminder, I noted last time that testing is not just a process of finding bugs. It's generally a process of alerting us to quality problems, some of which may not be in fact bugs, maybe inconsistencies between documentation and what's in fact done, maybe usability issues, maybe slow performance, etc. Non-functional characteristics. And generally we try to find important issues. We have limited time. We can't test everything. We can't even test a small fraction of all possible things. We can only confine ourselves to testing very small bits of all possible functionality. And we should choose judiciously what we test. We should choose carefully things that may be high risk, things that may be important, things that may be required frequently, etc. Okay, so I talked about some of these principles last time. I won't go through them in detail, but the testing process gives a lot of value in terms of its capacity to feedback information on quality issues. Testers can often spot early on, this part of the program is kind of soft. It seems to intermittently have these issues. Even if it's not a new bug report, it's helping developers clue in the fact that something may be off. Maybe a rare error they didn't see in their unit and integration tests is now more visible. Okay, so here we're trying to identify not just the problems in the program, but also process problems. What is it that left us vulnerable to these things? Why didn't we find them sooner? So that should be always on your mind. Now, one thing to bear in mind is that testing takes place at many different levels. Some of these levels are best left to developers and are traditionally left to developers. So if we look at these levels of testing, we can often, turn over here on the right, we can often establish a relationship. And this oversimplifies it, but it's not a bad diagram from a book I'll try to insert the citation to, between certain documents and certain sets of tests. So for example, requirements documents, which establish user requirements, perhaps derived requirements, things that are required to meet those user requirements at a technical level, perhaps, even though the user didn't explicitly request them. There's often a map between, say, acceptance tests. They focus a lot on requirements. They focus on system-wide functionality that the user requested. High-level design often maps to system tests, so tests that try out on an end-to-end basis whole areas of program functionality. Try a bunch of different features that exercise different areas of the program, like maybe it's loading a file and performing some manipulation with it and saving it away, something like that. Maybe it's opening up a connection to some database, executing a query, taking the results of that and performing an update and closing the connection. So these often involve system tests. The tests cross several pieces of functionality often, but are designed often to execute certain pieces of functionality that otherwise are under-tested or not well tested together. Detailed design documents often relate to integration tests. How do classes A, B, and C cooperate to achieve some task, for example? And then unit testing for particular aspects of methods within classes or functionality of a class as a whole. So of these levels of testing, which of them are typically left to developers? Yeah. Unit testing most certainly is. And in fact, typically developers will do some measure of integration testing. There's going to be some testing against, so if they're working on a certain class, often a class will have, as we say, high cohesion, low coupling. What do we mean by that? Who's heard that phrase before? Now, okay, what does that mean? Anyone give me a sense?
High cohesion means that a class's functionality is closely intertwined. You have methods that achieve a common goal for that class.
Right.
And low coupling is the dependence on that class on other classes.
Good, good. So generally speaking, speaking, a class will be accomplishing some clear, well-defined sort of type of functionality, and it'll do so often using its own internal methods, its own internal data structures a lot, and then occasionally it will call other classes. So it's quite common that one class will use instances of other classes to accomplish its job. At the most trivial level, it might use built-in classes that come with the Java standard libraries, things like string or hash table or what have you. And it might use other classes you folks have created. The idea with integration testing is you want to make sure that this class, particularly the other classes you created, that it plays together well with them. Because things can really easily fall through the cracks where, say, person A develops class A, person B develops class B, and then you have them, interacting, but certain functionality has fallen through the cracks. No one took responsibility for it. Or they implemented things in a way to work together, but with different conventions. So each of them has a reasonable implementation, just inconsistent. Maybe they use different enums to communicate the same set of information, and therefore they're not consistent in how they interpret certain values or what have you. So some measure of integration testing is typically done by the developers. And that links in with the issue of mocking that we'll be talking about, very important. Because if class A, if you're developing class A and it depends on class B, when you first want to test class A, you don't want to test it together with class B typically. After all, you want to focus on A's functionality. You don't want to focus on all these things that are going on in B. So often what you do initially is to mock out B. You create a mock of B. And there's mocking tools like JMock or Mockito, for example, which will aid in this. And then you can test A without testing all of class B. And you can test it with very simple responses from a mocked version of class B. And then at some point you will want to typically test class A with class B, an instance of A with an instance of B, for example. And a lot of that goes on at the level of the developer prior to their check-in. So they should be refreshing the code base for B and testing against it. But typically system testing, acceptance testing, the province, the test team, and some integration testing as well. The test team may get involved in other aspects too. Typically there's a mixture of automated and manual testing that goes on. So that's just to orient us. Any questions about this issue? And I hope you folks realize that since you folks should be coming closer to having your requirements documents thought through about what might be a requirement, say, in your first phase. I'm not going to say that's together yet, but you might be thinking about it. You could start to think about what an acceptance test would look like. That may not mean that you could fully write it yet, but you could start to think about sort of what a test would be that would lend some confidence that the program is working properly, that you haven't missed anything too absurdly. I should also note that as far as the smoke test is concerned, testing basic functionality, make sure you haven't broken something big, it's typically a system-wide test. It might be similar to some of the acceptance tests in the sense that it would run a couple types of sort of scenarios end to end. Okay, let's talk about this issue of testability. So one of the big issues here is that programs often have large amounts of internal state. So a couple of friends of mine went off and formed the company Orbitz back in the mid-90s. I don't know if anyone's sort of tickets through Orbitz before, but they're the folks who created it, some list packers. And it turned into a really large firm. And they do airline bookings, and they have a set of very sophisticated algorithms with the most important intellectual contributions being done in Lisp, and then a lot of the plumbing being done in C++, for example. And they look for flights that will get you from Saskatoon to wherever your destination otherwise legitimate. How would you test something like that? There's a lot going on. There's a lot of moving parts in there. A lot of internal state being maintained, and from the endpoint of the user, what they see is the request, and they see the response. They don't necessarily see evidence that it's done a thorough job looking. And when there are errors, when there's a problem with it, this is really brought to the fore, because it can be difficult to determine the cause of the errors. For people plugging it, for developers while they're testing their code initially. And generally speaking, when we build the system, we want to think about how to design it so that it can be easily tested and easily debugged. And we're going to be talking about these issues of logging and hooks as two examples of this, but two ways of facilitating that. But more generally, when we consider testability, we need to step back and realize there's some general principles that you folks have heard emphasized in other courses which aid it. One is the use of specifications. When you take the time in your program to say, this is what this method accomplishes. Given this, it will return that with these invariants observed. In the form of specifications. These can be informal or they can be formal. Often it's easiest to do informally, and in good libraries, like some Java libraries that you see Sun now Oracle providing, provide specifications of sorts. That helps promote testability because it helps suggest tests that can be easily run that would verify the what that it is being claimed by the specifications. In other words, the specifications describe what something does, not all the how by which it's accomplished. That's important because someone who is using a piece of code for which there's a specification shouldn't be counting on the how. The how should evolve according to performance considerations, and the person who writes that code should have generally the freedom to evolve exactly how it goes about accomplishing its goals. Maybe what it does is record, it takes in a number greater than or equal to 0, it returns the square root. The exact algorithm that's used in the approximations, as long as it observes a certain guarantee of accuracy, that should be up to the developer. Okay? And specifications, by describing the what, they allow the developer to evolve the how it's actually accomplished, the internal algorithms, the data structures. At the same time, those specifications provide a clear statement of properties that can be tested. If you do this, this is the result. Under these conditions, the exceptions will be thrown, etc. Another thing is modularity. I talked about before that if a program is a giant hairball and you have the UI intermixed with the database access, intermixed with logic at the application layer, and what we call business logic, it's sort of the logic of the domain involved, it's often really hard to test. It's hard to test it without going through a UI because there's no way to get access to that information, which is going to slow things down hugely and really, really complicate things. You'd like to be able to test the reliability of the database mechanisms, but to do so you have to go through certain types of functionality as supported by the UI, which may really limit what you can test. So having good modularity, where things are divided, as we say, separation of concerns, you divide out pieces of the program into different areas of the program which have their own responsibilities, that promotes testing. Testability. It promotes the ability to test effectively and test in a way that can permit high quality coverage of properties that you want to verify. Separation of interfaces from implementation. It's a best practice to not have code depend on the implementation of a class, to have it instead depend on an interface that class matches, and that allows the class itself to be changed, allows the class itself to be evolved over time without recompiling the things that depend on it. It also allows things to be mocked tests that will be written, even write them out, and then actually go about implementing it, make sure it passes those tests, and then you may refactor it. You may improve its quality. But we're going to talk right now about some other principles, or some other very practical sort of technical issues, which include the provision of logging functionality, providing hooks for programs, because these may not be things that have been emphasized in other frameworks. Later in the class, we'll come back to this issue of mocking, which is very helpful as an approach, particularly in the area of integration. Okay, so let's talk about this issue of test hooks. The idea behind test hooks is you have some code, and often there's a lot that goes on within that code that's hard to observe from the outside through the normal interface. The code may do something like find an airline reservation between 2 points. You want to know what's going on in the midst of that. Or it may, you may call request that it opens up some file on a tape-based system, and it goes and finds that appropriate file and loads it in. And you want to know, is this working properly? Would it handle an error of a certain type with respect to accessing that tape or accessing the disk or accessing the network? So there's some things that we can do that will enhance testing by providing functionality. So the idea behind test hooks is provide methods that you wouldn't otherwise provide as far as the general interface, but that can be used by tests. Okay? They can be used in the process of testing and debugging to find out what's going on inside this class, for example. These are methods which are normally being left out, which wouldn't be used by clients typically in the process of building the program, and therefore will want to provide a different interface for them. But they allow us to do useful things for testing and debugging. One very simple thing is to be able to enable logging. Perhaps enable logging of certain types of events specific to our class, so that when we're testing something's going wrong, we can see where it's occurring in the flow of execution. Where in this algorithm is it failing, for example? And depending on the context, you may sort of audit different types of information. Another issue would be browsing internal data structures. If you have a class that has a quite sophisticated internal data structure, maybe it's a hash table, and it should never have null keys in it, but you're not sure, maybe there's something about that that's causing an error. You might have a method which is provided to iterate through each thing in this hash table. Or you might have something that would simply check the property that there is no null keys in it. And you can call that method and it will verify that. So here, we might want to reveal to people who are debugging this code or to test a little bit of internal information. Now, it's very important that clients not see this. Clients shouldn't be counting on what internal data structures are using it. I mean general clients, other pieces of code elsewhere in your program. But your tests and your debugging may have needs to have a sense of what's going on internally. So we'll come back to it, but you'll provide this in a different interface. You won't provide it as part of the standard interface for this class. Here's another common, I won't say common, but another reasonably common need, trigger error conditions. So maybe you have a class that interacts with the network to establish database connections, or maybe to carry out database queries after connections are established, or maybe it accesses web services over the network, or what have you. But it doesn't have to be over a network. It could be it accesses things, B trees on a hard drive, or it accesses certain types of structures through I/O. In that case, you might want to be able to trigger certain error conditions. Just see how it would operate if it got something like high amounts of network congestion or drop network connection. So drop network congestion. you could create one. You could create hard drive errors in your testing, right? You could take a hard drive and you could bang it in the midst of testing. Bang it until it encounters an error and see if it behaves correctly. But that's generally not economical. The degree of sort of enjoyment that you get out of that may vary by person. But generally speaking, it's much easier to test things and much more straightforward to actually create these things synthetically. So the idea is, if you want to test how your code would react to certain rare errors, have a way of sort of injecting those errors, simulating those errors, and then you can see how it reacts. So you use some sort of callback mechanism or some other mechanism to trigger sort of a rehearsal of one of these errors, just like we do rehearsals of a fire alarm. And we see, okay, does it work properly? There's no fire. We don't light a fire and see how people go out. We simulate it, as it were. And so it is with these error conditions. Sometimes people create custom command languages for interacting with their functionality, so they can sort of issue commands to query what's going on in terms of data structures. That's more sophisticated, but it's sometimes done. But you could, ask, okay, what locks are taken out on some data? Check invariance, check connection state of a certain state between two things to find if it's still valid. Request the amount of data that's been sent. Examine the state of a cache being used to collect together recently accessed items. This would normally be invisible to a user. They wouldn't care whether there's a cache or not. They shouldn't be counting on there being a cache, a client of the software. But you, as someone debugging it or testing it, you may care about these things. Make sure the cache is working properly. Report back database data. You don't necessarily want the logic that checks the state of the cache to be external to the class. You might have a method in the class that's, check cache consistency or something like that. But the point is, you expose functionality that will check the correct operation of the code more readily, okay? Rather than it just being hidden purely within that class. So test hooks are something that you should be thinking about. Whether when you're building a class, for example, is there a way you could make this easier to debug? Now, an important thing here that I've alluded to, and I want to stress, is that when we have a class, call it a class C, it's a good practice. It's not one I'm always going to enforce, but generally speaking, it's a good practice if we do what's called separation of the implementation from the interface. So if we have an interface, call it I, of which this class implements that interface. I guess by UML standards it should be a dotted line. So this class implements this interface. And this interface, might have methods foo and bar and baz in it, and C would have implementations of foo and bar and baz. This is an interface up here, and so these aren't implementations. They simply say, for someone to claim themselves as a true I, as a legitimate I, they have to provide these methods. And generally speaking, there's going to be some specification along here, maybe it's just in English, that specifies what properties these have. So what foo does, what's its purpose in life, what the parameters mean, and what it returns based on the parameters, etc. What it accomplishes. Now, this I is an interface that can be implemented by many classes. And generally speaking, when we have client code, call it code in some class A, and maybe there's some method M in class A that wants to make use of this functionality, it will do so by referencing an I. Now that I may in fact be a C, but we separate that out. All it knows is that it's an I. It implements this. You folks have seen this before, right? In various classes. And this is a good thing with a capital A, capital G, and a capital T. In fact, it's just capitalize the whole darn thing. A good thing. All of the letters capitalized. Why is that a good thing?
I was going to ask you a question.
Good. Ask.
Oh, okay. Is there a rule of thumb for when it becomes overkill? Because obviously they're going to want an interface for every single class.
Yes.
Then that's
No, there's no question. And that's why I said, I'm not going to enforce this. Under what cases would this be particularly desirable? Let's start there. Okay, yeah. So when you want to change easily from implementation of C to an alternative implementation, right? An alternative to C. Maybe we'll call it D or C prime. Yeah, okay, C prime. So we might want to change the implementation, evolve this, and critically, we don't want this to have to be recompiled, right? So among other things, if this is being created by somebody else, this code, A, and we want to be able to evolve what classes we're using over here without having to go change those binaries, tell them, hey, go recompile all your code because our internal implementation has changed. If we want to lessen that propagation of changes over to their code, they could just depend on an I. We could substitute in a C prime for a C, and they never have to care. They don't have to care about recompiling because all they're counting on is that they're using an I, and C prime implements I as well. Okay, so that's a very important thing if we want to be able to replace this. And a key point here is that it's helping prevent the propagation of change. It's helping to lessen the degree to which changes over here come over here by depending on I. What's another case in which we might really want to use I here? Yeah. Okay, good. Yeah. So this gets to this whole issue of sort of cohesion and coupling. Often we'll want to have different packages compiled and distributed separately, for example. And we don't want to propagate across it. And we don't want, in general, this package, call it, PA, to have to, not Prince Albert, but, package A. And here's PC, call it. There's no Prince Charlie, but it could be. So here's PC. Generally, we don't want the people over here who are sort of associated with developing this package to have to worry about all the vagaries of what classes are used over here and their changes over time. So generally speaking, if we have use of one package by another, it's especially advantageous to go through an interface to give that other package the ability to evolve. What are other reasons we might go through an interface like that?
Common functionality, like data structures.
Yeah. So that's an area where there might be particularly common evolution, right? We might go from one sort of dictionary to another sort of dictionary. One sort of dictionary that's optimized for very sparse key sets to another that's optimized for, say, for repeat strings and for the ability to retrieve things very, very quickly. Maybe it's cache-based. So if we have a dictionary, for example, we might just want to count on it being a dictionary. Or if we have a collection, we just want to count on it being a collection, and then we could have any number of instances that implement that collection. Okay, so kind of goes to this notion that there's many alternative implementations. How about another thing, though? Anyone?
I think we've covered it, but essentially it had to do with other developers utilizing those.
Good.
That information. That's why an interface would be good, but we kind of touched on those in our explanation.
Right. And generally speaking, if you have different groups or different developers over here, and you want to minimize the coupling, you don't want to have to go to someone 5 times a day and say, oh, by the way, I changed this class to that one. Go and replace all instances where you refer to that class with the new name or something. Oh, I happen to change it to this other name. Oh, I refactored that this this method over, so now you have to recompile. So generally, if there's different responsibilities or roles and responsibilities within your project, trying to minimize coupling across them is good. But there's another reason yet, and that has to do with, there's two additional reasons I can think of off the top of my head. One is, has anyone here used the Spring framework? Does that ring a bell? Okay. Or have you used inversion of control, dependency injection? Does rings a bell? Ring a bell? No. Okay. So I would advise you, before you leave the august confines of this revered institution, to acquaint yourselves with those frameworks at least a little bit. In 470, I used to cover dependency injection and inversion of control.
What were those?
Okay. Spring. Spring is a very common framework used for these. But the general technique is known as dependency injection and version control. It goes by the name of the Hollywood principle. Don't call us, we'll call you. Okay? And the idea here is that increasingly software is being constructed in a different way than when you folks were young. Or when I was young, and the world was still cool. So one issue is that there's fewer cases where you're going to be building up a system entirely from scratch, and more cases where what you're going to be doing is crafting components that are, and I'll use this word, sort of placed into a system, a sort of an ecosystem of objects that's operating. Okay. Now that sounds awfully abstract, but what I mean by this is that you're going to instead of creating a system entirely from scratch, you're going to be reusing broad frameworks where your customizations of it are fairly small pieces in the grand scheme of the overall functionality of the system. And that overall system that you're plugging your stuff into will take care of a huge amount of responsibilities that otherwise you'd have to worry about. It may be persistence, for example. It may be security. It may be issues of transactionality. It may be issues having to do with sort of the authentication and authorization. It may be logging. All these sort of things that you don't want to have to worry about will be sort of provided automatically for you. And what's going to happen is that you provide modules that plug into the system, and the system will call your modules at certain well-defined points to accomplish the functionality. Okay? Now, those are in 394. We'll see this actually in a simulation context, where you're sort of tailoring little things they'll plug into it. But you'll see this in other areas too. And increasingly, this is how robust applications in many areas are being built. You customize small portions of it, and then it takes care of the rest. And one of the most powerful features of these systems is that they allow you to evolve your system without recompiling. Okay, so and you get things for free. You get transactionality, you get scalability of your system. So those atomicity constraints, the acid properties, atomic, consistent, independent, durable, that you want to achieve with databases are maintained, and it's done in a way that that is fairly easy for you to use. So what you do is you create a class C, perhaps, which implements an interface I, and then you tell the system in a config file, a configuration file that's on, some file share. You have a config file, and it says, I want to use class for my implementation of the, some sort of UI class, UI.class equals, C or something like that. Okay, and C has to implement a certain interface. Maybe it's called I. And the beauty of this is that in this config file, you could specify, without recompiling the program as a whole, you could then later specify, C prime. and it'll work just fine. Just by changing that config file, you could change around what classes you want to mix and match within your program. Now, if you go and you look, you'll find Spring is quite popular as a framework for implementing sizable systems because it allows you to do a small bit of work, plug into this whole well-tested, well-debugged ecosystem of objects. It turns out the debugging is more complex for these types of systems because you often have to have a sense of how the overall system is operating and under what conditions it will call your methods and so on. But it's really this implementing interfaces that allow you to make use of these things. So I don't know how many people here have done, how many people have used Eclipse here? Okay. How many people have built Eclipse RCP application? Anyone? Okay. If you want to customize Eclipse, it turns out you can get the goodness of Eclipse for your own applications with a modest amount of work. Okay.
Is this sort of like how AnyLogic is?
Yeah.
Oh.
Exactly. So you can get the framework of Eclipse around your own applications, the look and feel of Eclipse, the ability to get access to the help system, to use a whole sort of suite of different things that Eclipse supports as far as plugins, etc. You can get that around you by adhering to this sort of scheme. So as long as you provide classes that match certain interfaces, they can be plugged in and they can sort of interface with Eclipse and do the necessary work so that they get exposed as Eclipse windows, etc. And increasingly, folks, early in your professional lifetime, this is now that this stuff is actually quite hot. And the sooner you get exposed to it, the better. Because when you get out there, you may well find yourself working with these sort of systems. So they're systems that are appearing in an increasing way because of the needs for robust system functionality without requiring a huge amount of re-implementation effort. So Spring is one example of a config-based system. I think I may actually do a lecture on these later on if there's interest and if it seems germane to the projects, okay? But it's something to be aware of. So that's one additional issue about why you may implement an interface here. But another issue is mocking. It turns out that by mocking out, so you can create a C prime, which substitutes for a C, and all it does, for example, when you call a C prime, all it does is it records what it's being called with, the parameters, call C, and then records the return values and returns back. And that's a sort of interception sort of deal. So you could sort of essentially spy on the interactions with C through an intermediary, an interception mechanism, because you're only dealing with C through an I interface. C prime implements that as well. So you just have this interposer C prime, which intercepts calls to C and extracts extra information and records it from that. Very nice for logging, for example. Generally speaking, implementing interfaces will be very handy if you're seeing fast evolution, if you need possible multiple implementations of it, if you want runtime flexibility for changing implementations of it, and finally, if you have division of responsibility within your program between different units and you want to minimize coupling between them, okay? Those are some compelling reasons why you might want to implement an interface. Another reason is if you have multiple variants circulating at the same time, which all share certain common features, and they need to be sort of plugged and played into a common infrastructure. So you might have, for example, a set of classes which represent different commands within your system, and these commands could all be invoked by menu items within your system or by key presses or whatever. And each of those commands might implement a command interface. And that allows them to then be placed in certain data structures, that allows them to be looked up. You know, you can look up all the commands, ask, okay, does it match the invocation command for that for this particular command or what have you, ppress for that command. So generally speaking, if you want to be able to capture commonality among things, it turns out interfaces are a more flexible way of doing it than subclassing. Okay. Subclassing has some restrictions because you can only have one superclass in something like Java, whereas you can have multiple interfaces you implement. A key thing here, though, is that when it comes to test hooks, you won't want to add those methods which are internal spy methods. Let's call it spy. You don't want to call that put that spy method in your main interface, because you don't want the clients of this to be using spy, to be counting on this. This is a kind of implementation detail. So if you have a test which you want to use spy, generally speaking, you could have a iTest interface, which is implemented by this, which has a spy method, and then the test could call this through this guy here. Alternatively, the test could work directly with an instance of this class, knowing the test is going to have to be recompiled if this changes. Okay, so test hooks, you don't want to just put them into the main interface, because they're not functionality that are exposed to clients. They're functionality exposed to testing and for debugging. Does that make sense to people? Okay. Okay, let's talk about logging. How many people have implemented loggers at a significant level within your projects before? Has anyone here done some logging? Okay, good. A couple people. Logging is a process of recording a record, a trace, as it were, of events during program execution. And this recording can be made to different places. Often you want to make it to several places at once, in fact. Have a more persistent record, perhaps in a database or a file, maybe also printed out on a console, etc. And typically logging is notable because it can be performed at a variety of levels of detail. Okay? And I happen to like the Log4j framework as a very, very simple framework, but there's more sophisticated frameworks out there as well. I'm going to talk about, and other very popular frameworks, I'm going to talk about Log4j. So this is the sort of type of logging information that we might get. This is from Dustin's very good book on effective software testing. So here we're logging some information on important events that have occurred. Connection to a database, reporting back it's reporting the timestamp of it, the machine involved, which server it's connecting to, reporting back the result of it, and then some functionality trying to work with that connection, etc. So if it crashes in the middle of it, you can look what the last logged message is, and that will give you a pretty good hint as to where it crashed, in what step of this whole process it crashed, which can be very helpful for debugging. It can also be helpful for testing, that you can look back and see, okay, what steps has it actually gone through? Did it actually hit the functionality I wanted it to hit, I intended it to hit? Okay, let's talk about Log4j. Log4j has a couple nice features of it. And by the way, folks, these are enabled by this sort of framework we were talking about, the separation of interfaces from implementation. So one thing is you can use config files to specify logging characteristics. You don't have to rebuild. Okay? You could say, I want this run of the program, I want it to log, I want it to send a log via email and to post via HTTP to this server, and I want it to go to this console. You can log at different levels, and you can change that in your config file, how detailed you want the logging to be. You want to get things at a very, very low level, so voluminous, lots and lots of detail on what's going on, or just the most urgent errors, fatal errors, or do you want to get something intermediate like warnings, etc. A logger here can be associated with multiple output streams, and it can upload things to the server, can send mail via SMTP. It can filter out information that doesn't match patterns, only pass on certain information. So the actual logging class is very, very simple here, trace, debugging, info, and you could call these methods. So you might call, for example, you might get a logger, and then issue a warning associated with it, some call and you log in this way. The deal is that, you know, a given one of these, say the warn and the debug, may not, for a given run, they may not put things out because you're only set to actually report things that are at a higher level for that run of the program. This is what a config file can look like. So here we're setting the logger level, how much details it can report, and how are we going to report that, to what mechanism. Well, here we're going to the console here, and what pattern, what layout do we want to use for the information we report? Where is the time going to be, for example, or the information about the error message or the server on which it's occurring. You can suppress certain information. For example, print only messages of level warn or above for certain modules of the program and not for others. So you can have the reporting detail be module specific within your program, which is useful. You can also have it going to multiple outputs at once. So for example, here it's going to a file appender as well as a console appender here. So big picture here, config file gives the specification of what to log. You run your program after changing the config file, and it will log different information. No recompile needed. You don't have to go in and scatter comments through your code, comment out, logging things in your code. It can all be done through a config file. And this gets to this issue that I urged earlier, which is collecting automatic fault reports. Quite easily done when you reflect on the fact that log4j, for example, allows you to support reporting via HTTP. So you can report to a server via HTTP. By the way, why report via HTTP? Students sometimes don't have the historic context in this. Why would we, if we were running a program and we want to report some error messages back to the mothership, so to speak, we want to report it back to our server, why would we go through HTTP?
It's commonly known for.
Exactly. So you may not notice it as much in an academic environment because things are pretty open port-wise compared to a lot of corporate situations. But for a lot of corporations, things are really tightly tied down as far as what ports are left open with respect to the external world. And it's to reduce risk of security vulnerabilities in large part. HTTP port is commonly left open in organizations so that packets can come in and retrieve things from web servers and so on. So if you go through HTTP, it's less likely to be blocked by a firewall around some organization that holds the mothership of the database, so to speak. Okay. Any questions on this material I've covered thus far before I just make some beginning testing tips? So this issue of testability, is that something people can appreciate the value of that? They're thinking about it? These are rough and ready rules. I'm not going to say every class needs, to be laced with testability information. But it is something that I'll hope to see, particularly for more sophisticated classes where there's more going on in the methods, more going on between methods. So one thing I want to warn you about, stay away from that. One thing I want to warn you about is, and this will get to some technical guidelines I'm going to see. One of the reasons this class is always so interesting is because I get to see a lot of student code. And
interesting with scare codes, right?
yeah, yeah. Interesting is a choice word here, and sometimes it elicits difficult mannerisms from me. But it's notable that students in this class, I've seen one pattern that I'm just going to warn about right now ahead of time because I'd like to urge you against it. It's a common pattern that comes up about once every 3 years or so in this class. And it has to do with, in this course, and it has to do with a class where basically the class is being used like a C data structure. How many people here have done C programming? Okay, good. You folks know what I'm talking about. Then in terms of C data structures, the class is basically its methods are all super low level. So you have get name and you have set name, and then you have get whatever it is, like get address, set address, and all that's being used. The only way in which the sort of object-oriented features are being used here is to have sort of methods which hide the details of the internal fields that are used, but it's almost a one-to-one mapping. There's really no intelligence being built for the class, and often what happens is the logic associated with this class, the business logic having to do with everything that has a name needs to have an address associated with it, or what have you, or if you're not allowed to change the name, that all gets submerged, and often that gets done somewhere else outside of this class. And so all that sort of logic about what's allowed for the class and so on isn't managed in the class, and there's no high-level methods that do something really significant to this class. It's just a data structure. It's just being used to kind of keep a couple pieces of information. And frankly, folks, this isn't, by my view, this is not a lot better than just having public fields that are visible from outside that you can frog by setting and getting them. There's not a lot of real encapsulation going on here. You've kind of exposed what the fields are in this mechanical way. And sure, you don't have the fields being public, you have the methods being public, but all the methods do are get and set the fields. It's kind of a shell game as far as I'm concerned. What you really want with a class is you want something that has high cohesion. It has certain responsibilities. It takes care of maintaining and checking certain invariants for itself. It takes care of some sort of functionality that's meaningful for objects of this sort, rather than delegating all that to external things that use this in the same way you'd use a C data structure. So this sort of pattern is distressingly common. And one thing that I see a lot with it is you create one of these, and then all it's done is you create one, and then you set, and then later you read them. And effectively, it should be read-only. You should be able to create this thing with its field set, and from then on, never be modified again. But instead, you always have this possibility that you could call set here. So no one who's using this class can count on it being, being read-only, being immutable. Often, folks, you're going to want to look for opportunities where a class can be immutable, cannot change. That is a good thing, with also all capitals, for reasons we'll be talking about later. Immutability lets you build abstractions on top of the class, build other classes out of these components in a much more reliable way. It lessens the risk of bugs greatly. I'm not going to say all classes should be immutable, far from it, but where you could see opportunities for immutability, for a class being created up front with the information it needs, and then from then on being unchangeable, it will be good because it will lessen headaches for you. So you should be looking for opportunities like that, and please try to stay away from this issue of just using a class as like a collection of fields and just exposing them with methods. This is not sort of using object-oriented programming techniques and software engineering to its strength. This is kind of an impoverished version of what a class is. Okay? Yes?
So an example of modifying that class to essentially do that, hold information in person.
Yeah.
You would have a constructor.
Yes.
And instead of the constructor just being new and an empty constructor
Yes.
setting all those fields,
Yes.
you have immutable fields.
Yes.
So say if there was a requirement to create a person, the person needed a name,
Yes.
needed a password, and needed an email address. Those
That's right.
three things would be passed to the constructor and
Upfront.
therefore become immutable.
That's correct.
Then you can do the get and the set for additional information.
Well, generally, you're going to minimize the sets there.
You try to, yeah.
you try to minimize the sets, and the advantages of mutability are very significant, and I'll see if I can feature them. Maybe I'll do a little song and dance at the beginning of the next lecture. But yes, you try to minimize the degree to which that class would then be modified subsequently, and that allows the other classes which use it to count on, okay, if they check the name was this at this point, they don't have to recheck it periodically. They don't have to go look for it's constantly updating. Right. And that allows you to count on certain properties that can only be checked, say, in the constructor. They don't have to be checked again whenever you're calling the class or something like that. And it's just a lot clearer, because when you're looking at code that involves modification of data, it's a lot more complicated to think through how it works, because you have to be thinking, okay, where's all the places it could be updated? Where did it get updated last? If you're dealing with code where, okay, this is created, from that point I know it's a constant thing, it's one significant less thing to worry about, okay? Yeah?
I just have a quick question.
Sure.
In this case, for the example of where, person A has the possibility, like you're talking about making it immutable. So let's say we create person A that gets created in the class.
Yeah.
And okay, I like that to change what happens is, but let's say I'm just saying things happen and person A comes up and say, okay, I'm going to change my life.
Yeah, well, let's
destroy the object, copy the
yes, let's be very clear about this. I'm not saying every object has to be immutable.
Yeah.
What I'm saying is that from my observation in student projects, 9 times out of 10 you have mutability. It's unneeded, actually. Okay, maybe that's an overstatement, but in a lot of cases, what I see is students exposing this functionality to modify things where it can be created upfront and kept in that way. If you have a case where there's data that needs modification, you can do it with immutable objects, where you have this sort of you create it for a while with this, and then you have a separate update step, and then you create a fully immutable version later with the new updated name. So you could sort of copy it over in that way. But obviously, there are cases where you can have mutating state, and you don't want to claim it's immutable then. It's just that if you can use immutability when it's a clear property, or when you can get away with it, it will save you headaches, okay? It will significantly reduce the amount of effort to understand your code. It will reduce the likelihood of bugs creeping in. It will help you verify the correct operation of your code in peer reviews. It's generally a good thing, and it turns out it helps scalability for reasons I don't have time to go into here. Turns out that immutability is one of the things that can really enhance scalability within a system. And stateless objects, as they're called, are one of the classic techniques for allowing systems to scale outwards when supporting large numbers of users. Okay, so this is something to think about. All I'm saying is try to avoid gratuitous use of sort of exposing data structures in this way by just one-to-one mapping with method names, and try to avoid, you know, needlessly, gratuitously having things be mutable. Okay, so those are some comments. You'll probably see more comments of that sort when I get to look at your code. I will on occasion, and I'm going to have to ask your pardon for this. I will on occasion, without revealing where the code comes from, show snippets of code and critique them. Okay? I will do so in a way that will make every effort to avoid revealing who it's from or anything like that. But there's lessons to be learned here, and I think one of the most important, from my understanding from what students have told me, one of the most important sets of realizations students in this class have had has been from those sort of reviews of code where I will comment on code that's been handed in, how it can be improved. That has led to material benefits for the student teams in terms of cleaning up their code base. So we will do that from time to time. And I would welcome you to bring examples to me and say, you know, we're not sure how this should be structured. Could we do it this other way or what have you? I'm happy to discuss that. Okay, I think that's that's all we have time for today. Today at 4 o'clock, of course, per my comments, we have the discussion with the previous project manager. That's going to be here, 205A, as normal. I'm not planning to record that, so be sure to take good notes. I won't be present for that presentation. Okay?
394 is at 4:55.
Yes. For those anyone who's in it, 394 is at 4:55 today.